A major component of calculus is understanding the notation and the terminology. So there are many ways to denote the derivative of a function y equals f of x. Besides f prime of x, the most common notations are y with the little slash out beside it, which indicates y prime. It's nice and brief, but it does not name the independent variable. The independent variable is the one that acts as the x value. dy dx, where you write it like this, is either just said dy dx or the derivative of y with respect to x, and it's nice because it names both variables and uses d for the derivative. If we say df dx, or the derivative of f with respect to x, it emphasizes the function's name. So if you have 3 or 4 functions and you name them different things, this is a nice notation because it emphasizes the function's name. We know that like f of x, g of x, h of x, those are all just taking the place of y. So this is just a very general, and these sort of get more specific. If we write it this way, where we say d dx of f at x, or the derivative of f at x, this is the emphasis that differentiation is an operation performed on f, and this is also the notation that is typically used to give you generic formulas for the derivative, because we will be learning a lot of like kind of shortcut rules for derivatives as they get more and more complicated so that you don't have to use the limit process every time. So when we give you a generic formula, you will oftentimes see it notated this way. Let's find the derivative of f of x equals x cubed plus 2x. So this is a little more complicated because it's to the third power. But what's nice is we're only being asked to find the general derivative. We're not being asked to find the slope or the slope of a tangent line or plug anything in. So when we finish this, unless it is a line, it should still have x's in your final answer. So let's start with our formula. F prime of x must equal the limit as h approaches 0. And I chose the notation f prime of x, but you could have used df over dx. Of f of x plus h, so that would be x plus h cubed plus 2 times x plus h. So that's f of x plus h minus f of x, which is our original function, all divided by capital H. So the hardest part of this is going to be getting that x plus h cubed. And some of you may or may not know a shortcut for that. I'm betting most of you don't. So let's just come out here and let's just kind of work on it together. If I want to cube x plus h, that's the same thing as x plus h, x plus h, x plus h. So if I multiply the first two together, that will give me x squared plus 2xh plus h squared. And then I just need to distribute the x plus h to all of that. So then I have x squared times x is x cubed, x squared times h is x squared h, 2xh times x is 2x squared h, 2xh times h is 2xh squared, and then finally I need to distribute the h squared. H squared times x is xh squared, and h squared times h is h cubed. So, cubing out that function yields 1x cubed plus 3x squared h plus 3xh squared plus h cubed. And that's going to be the brunt of your algebra there. Just making sure you can get that binomial cubed out properly. If you remember the binomial theorem and Pascal's triangle, you can do a pretty decent job of that using just that. So if you remind me later, I'll give you a quick little tutorial on that. Okay, so here's where we are. We have all of this. Then we need to distribute the positive 2. And we need to distribute the minus sign. and divide it all by h. Then we'll go through and we will clean up and cancel what we can. So the x squared, the x cubes should cancel. The 2x and the negative 2x should cancel. And it looks like everything else still has h's in it, right? Okay, so let's write down what we have here. We have 3x squared h plus 3xh squared plus h cubed plus 2h all over h. Let's pause for a second, make sure everybody's caught up. Now all we need to do is factor out an h and cancel it with the denominator to make it 1. That leaves us with a difference quotient of 3x squared plus 3xh plus h squared plus 2. And if I apply the limit as h approaches 0 to that difference quotient, and I let all my h's go to 0, what do I get?
3x squared plus.
So all of that work for a derivative of 3x squared plus 2.